Hey everyone, welcome. Have you ever opened your physics textbook, flipped to that very first chapter on units and measurements, and just thought, ugh, really? This is literally just a boring vocabulary exercise? Well, look, it's completely understandable to feel that kind of way. At first glance, memorizing all these random units feels like a massive classification chore. But today in this explainer, we're going to completely flip that perspective. We're going to see how units are actually the literal building blocks of the entire physical universe. And getting this right, it's going to pay off big time throughout your entire physics journey. So let's get into it. Okay, so here's the absolute secret to this entire topic. Every single physical quantity you're ever going to measure or, work with in physics falls into one of two buckets. It's either something you measure directly, all by itself, or it's something you calculate from other quantities. That's really it. Physics isn't about memorizing an endless alphabet soup of letters and symbols. It's really just about spotting what stands completely on its own as a foundation and what's built out of those foundational pieces. Once you see it like that, I promise the whole concept of units just magically clicks. Right, so let's dive into that first bucket, fundamental units. The one keyword you really need to drill into your head here is independent. A fundamental unit, sometimes you'll hear it called a base unit, stands entirely on its own 2 feet. It doesn't need or depend on any other unit to exist, and you absolutely cannot break it down into anything simpler. It is the absolute bedrock, the literal foundation of the house. Now, the International System of Units, or the SI system, officially recognizes exactly 7 of these fundamental quantities. Think of these as the 7 pillars of physics. We've got length measured in meters, mass in kilograms, time in seconds, electric current in amperes, thermodynamic temperature in Kelvin, amount of substance in moles, and finally, luminous intensity in candelas. The absolutely crucial takeaway here is that literally everything else in physics, every single force, every massive burst of energy, every intense amount of pressure, ultimately boils down to some specific recipe of just these exact 7 pillars. So now that we've got our base blocks, what happens when we start snapping them together? Well, we get derived units. Derived units are made purely by combining 2 or more of those fundamental units, usually by multiplying or dividing them. They aren't independent of all. Let's look at speed, because it's the absolute simplest example. Speed is just distance divided by time, right? Distance is measured in meters, which is a fundamental unit. Time is measured in seconds, another fundamental unit. So smash them together, and the unit of speed becomes meters per second. Boom, you just arrived a brand new unit. And this brilliantly illustrates how we use those 7 independent building blocks to construct much more complex physics concepts. We're talking about things like the Newton for force, the joule for energy, the Pascal for pressure, and the watt for power. Whenever a physical quantity is defined by an equation, its unit is just mathematically derived from whatever units are sitting right there inside that equation. It's like a giant puzzle where all the pieces perfectly interlock. Okay, let's actually deconstruct one of the most famous units in all of physics, the Newton. So Newton's second law tells us that force equals mass times acceleration. Mass is measured in kilograms, acceleration is in meters per second squared. So, logically, force has the unit of kilogram meters per second squared. But honestly, that is a mouthful to say every single time. Since this exact combination is used so constantly, we just gave it a cool nickname, the Newton. But don't let the name fool you. Underneath that shiny label, it is purely just our fundamental blocks. The name is literally just for our convenience. Let's translate all this abstract stuff into everyday real life, because, well, physics is happening all around us all the time. Think about your car's speedometer reading something like 80 kilometers per hour. That right there is a derived unit. It mashes up a unit of length, the kilometer, and a unit of time, the hour. Even if we convert it to standard SI units to get meters per second, it is still just a calculated ratio of length to time. So neither kilometers per hour nor meters per second is a base unit. They're built from the ground up. Here's another super common example. Imagine you're lifting a heavy 10-kilogram box off the floor and putting it onto a shelf 1.5 meters high. You're doing work against gravity, right? First off, we find the force. Mass times gravity gives us about 98 newtons. Then we calculate the work. Force times that distance gives us 147 joules. The mass in kilograms, the height in meters, those are completely fundamental. But the Newton for force and the joule for the work you just did, totally derived from those basic fundamentals. They simply don't exist without them. Let's try just one more, just to make sure we've got it locked in. If you have a pressure cooker at home, the pressure building up inside is typically around 200,000 pascals. Pascals sounds very official and fancy, doesn't it? But once again, it's just a derived shorthand. Since pressure is just force divided by area, when you break it all the way down to the bottom, 1 Pascal is really just 1 kilogram per meter per second squared. The kilogram, the meter, and the second are actually doing all the heavy lifting behind the scenes. So, you might be wondering, why does this distinction actually matter? Can I just memorize the names and be done with it? Well, no, and here's why. Dimensional analysis. It sounds intimidating, but it's actually a superpower. Knowing your base units lets you physically check if a formula you've just written down is actually valid. You do this by checking if both sides of an equation balance out exactly. If your derived unit on the left side doesn't mathematically reduce to the exact same combination of base units on the right side, well, you immediately know your formula is wrong. It's the ultimate built-in cheat sheet to check your work. Now, there is a massive trap that so many students fall into here. It's a hugely common misconception that derived units, like joules or pascals, are just arbitrary names that have absolutely no connection to the base SI units. But as we've literally just seen, what's actually true is that all derived units are exact mathematical combinations of those 7 SI base units. So, rule of thumb, never ever let a fancy capital letter name trick you into thinking it's a fundamental unit. It's a disguise. Let's run through a quick recap of the most common pitfalls so you don't make these same mistakes. First, thinking there are only 3 fundamental units, like just length, mass, and time. Look, while those are super common in basic mechanics, remember the full SI system has 7 pillars. Second, confusing named units like newtons with fundamental ones. Always stop and ask yourself, can this be broken down further? Third, assuming an everyday unit like kilometers per hour is fundamental just because we use it all the time. It's a ratio, so it's strictly derived. And finally, mixing up your systems. The centimeter is from the CGS system, the meter is SI. Pick one system before you start calculating or things are going to get messy really fast. All right, practice time. Let's put your brand new physical intuition to the test with a question straight from our frequent questions list. Based on everything we've just unpacked together, is the Newton a fundamental unit or a derived unit? Take just a second to think about what stands alone and what is built from other pieces. Got your answer? Well, if you said derived, you hit the nail right on the head. The Newton is purely a derived unit. It comes straight out of Newton's second law, force equals mass times acceleration, and that gives us the underlying unit of kilogram meters per second squared. Like we said earlier, the Newton is strictly just a highly convenient name tag for that exact combination of fundamental blocks. Okay, let's do one more practice question before we wrap up. And honestly, this one's a bit of a curveball. Do you happen to recall what the supplementary units are in the SI system? Think back. They occupy this slightly weird, different category entirely separate from our main 7 base pillars. Any guesses? So the supplementary units are the radian for flat, plane angles and the steradian for 3D solid angles. And what's really fascinating about these is that, mathematically speaking, they are technically dimensionless ratios. Take a radian, for example. You divide arc length by radius to get it. But since both of those are measured in meters, the units actually just cancel each other out entirely. But we keep them around as named units purely for clarity when we're doing complex physics formulas involving angles, like when you're studying wave physics or optics. It just keeps things neat. So I want to leave you with this final thought today. If absolutely every unit, force, and burst of energy in physics is built from just 7 independent fundamental blocks, how does that change how you look at the scary equations in your textbook? Because frankly, you aren't just memorizing random letters anymore. I really encourage you to start hunting for the base units hidden inside every complex formula you encounter from here on out. I promise you, once you start seeing the actual building blocks, physics becomes way less about rote memorization and a whole lot more about simply understanding how the puzzle pieces fit together. Thanks so much for joining me on this explainer, and keep building that intuition.